Okay. All right. So now I guess it's week 2 of our summer session, which translates to week 3 in regular time. Okay. So it's like this week is weeks 3 and week 4. And so we are covering chapter 4 in the textbook on classification. And so you guys are working through your homeworks on chapters 2 and 3, and then this week I will assign homeworks from chapters 4 and 5, and yeah, this is a great textbook. I think, you know, if you go out on like forums and you look up like, I want to get into data science and machine learning, that they'll always recommend this first. This, and then kind of the other book, The Elements of Statistical Learning. So the Elements of Statistical Learning is a little bit, a little harder, okay? A little more mathy, all right? And this one's the easier version, all right? So Elements of Statistical Learning is often used as a textbook in grad school. So if you go on to grad school to study, I don't know, statistics, machine learning, data science, that kind of stuff, you'll probably have elements of statistical learning, and then, but then kind of this is the nicer version of it, the introduction to statistical learning. And we don't do a ton of math here, just a touch of it, okay? So anyway, we're in chapter 4, classification. This is basically the table of contents from the book, all right? And the big idea is our response variable is a categorical variable, okay? So last week we looked at linear regression. Linear regression, the response variable is numeric. It was a quantitative variable, and you added things together. You know, you take each of your predictors, you multiply them by a beta, and then you add them up, and you get some numeric response. This time, the response that we're looking at is categorical. It's this, okay? And so in this chapter, we'll look at logistic regression and linear discriminant analysis, which is just another way, like a simple Bayes classifier, really. And then k-nearest neighbors. If you took my 102B class, we've talked about the Bayes classifier, which is, you know, very similar to linear discriminant analysis. And then other methods that we'll talk about for classification will be the generalized additive model and the tree-based methods like random forest and stuff, and then support vector machines. That will come later in the text. But today we'll look at logistic regression and stuff. Okay, the data that we are going to use for teaching is this simulated data set. It's not a real data set. For teaching, we often use simulated data sets because they're cleaner, and you don't have weird outliers, and you don't have just stuff. But that's like the drawback of teaching things, is that like when you go out into the real world and you experience real data, it's always a mess. And you have to like think and clean up, and you can't just start applying some of these things right away. Like some of it is just like removing typos, and you're going to spend like hours doing that. Maybe with regular expressions you can speed it up a little bit, but anyway, okay. So anyway, the idea here is people have credit cards, and not everybody makes the minimum monthly payment, okay? So around 3%, so 1 in 30 people will miss the minimum monthly payment, and that will hurt their credit score, and we will say that these people defaulted on their credit card payment, right? So default, I always think of default as like the settings that come on your computer if you don't change anything. It's just basically what happens if you take no action, right? So if you take no action on changing the settings on your computer, you get your default settings. And if you take no action on paying your credit card, okay, which in that case is a bad thing, you have defaulted on your payment. Okay, so anyway, default yes or no. In this case, we don't want to default, but 3% of people do. And we can take a look, start by taking a look at two input variables, and these are numeric. The annual income of the person, and then their monthly credit card balance, how much balance is carried on the credit card. And so, you know, this is simulated data, and so here the balance goes anywhere from $0 to $2,500. Okay, and then the income goes anywhere from 0 to, I don't know, $60,000, maybe $70,000 in terms of annual income. All right, so it's not, again, real world, this would be a huge mess, right? Because you're gonna have people with like income $1 million, and then you have to like redraw your entire graph because, you know, 90 whatever percent of people are under 100,000 or something, and then you got a million, which is like 10 times bigger than that. So anyway, simulated data said this is fine. And what do we see? Just so the little pluses means they defaulted, and the blue circles means they did not. In order to make the plot more visible, they didn't draw every single blue dot, okay? Because there's like 30 times more blue dots than pluses, orange pluses, but that's not how it appears here. They appear equal proportions. So we only drew like, I don't know, probably 1 in 30, 1 in 20 of the blue dots, and then we drew all the orange pluses. So anyway, what we see is that as far as income goes, you know, at lower income versus higher income, in terms of like the rate of defaults, it doesn't seem to change much, okay? But as far as the balance goes, we can see for low balance, no one's defaulting, and then at higher balances, everyone's defaulting, okay? So we see, you know, a much stronger relationship between between default, who defaults and who doesn't, based on balance, okay? And then we can make a few box plots. This just summarizes what I'm going to say. And we see that if we look at the balance on who defaults yes and no, we can see for those that do default, their balance is much higher. Those that don't, the balance is much lower as far as the median and things like that. And then as far as income goes, those that default and those that don't default, the income distributions are relatively similar, okay? So this indicates to us that when we fit a model, we should probably use the balance as a predictor versus income, okay? Now, again, simulated data, so we have this very clear, stark difference between the two groups. Real data is almost rarely as nice and clean, okay? Before we get into running such a model and making a prediction based on that, the question is, why can't we just use linear regression, okay? Why can't we just say, let's make this number this equal to this category, right? And so, some silly example, we could say, you want to predict what the medical condition of a patient is based on certain symptoms. And just to keep things easy, let's say the only 3 diagnoses are stroke, drug overdose, or epileptic seizure. And if we said, let's just use linear regression and Y be a numeric response, we could say, well, let's let 1 be stroke, 2 be a drug overdose, and 3 be epileptic seizure. But the problem with this is that as soon as you use numbers, there's an automatic ordering of these values, okay? We're saying that a drug overdose is something in between a stroke and an epileptic seizure, okay? And that doesn't quite make sense, and that the difference between a stroke and a drug overdose is pretty much the same as the difference between a drug overdose and an epileptic seizure, because the difference is 2 minus 1 is 1, and 3 minus 2 is 1, and so we're saying there's basically the same difference between these two things, numerically, whatever this thing is measuring. And that probably doesn't quite make sense, okay? Somebody else could take the same data and say, I want to order it this way. I want to do 1 be epileptic seizure, and 2 be a stroke, and 3 be a drug overdose, okay? And is there anything wrong with this? Well, if this is valid, then this seems just as valid, okay? And so, trying to take something where you've got basically these categories that don't have an implicit ordering or an implicit arrangement, it doesn't make sense to turn them into numbers and say these should be, we should predict them numerically, okay? In another example, and I'm not doing this, but you might have an image of a number, and you want to predict what number this image is. Is it the number 0 or the number 1 or the number 2, okay, or the number 9, right? And in that case, we might feel like there is an implicit numbering thing, but the truth of the matter is that the symbol used to represent the number 2 and the symbol used to represent the number 8, there's no ordering, there's no implicit ordering for the symbol used to represent these numbers, okay? So it's so if you wanted to predict what digit some image represents, it does not make sense to use some kind of linear regression or numeric response, because here you're trying to associate a visual symbol with basically a digit representation, and it's not an actual, like, the visual symbol does not actually carry the value of the number, if that makes sense, okay? We're just trying to correctly put them into different categories of, these represent this symbol, and these images represent this symbol, and these images represent this symbol. And it's not to say that the picture for the number 6 has more than the picture for the number 3 or something like that, okay? I don't know if that makes sense. So we have a couple exceptions to this kind of rule about not representing categorical things with numbers. You could have a numeric coding could work for ordinal categories, okay? And ordinal is like that, is a hybrid between something in between numeric response and categorical response, where there is an ordering. So something like small, medium, large. Somebody could say small is 1, medium is 2, and large is 3, or something like that. Or maybe small is 8, and medium is 9, and large is 10, or something like that. There could be some kind of representation there. If you're talking about, like, how much do you agree with this statement, and it goes anywhere from strongly disagree, moderately disagree, slightly disagree, neutral, slightly agree, moderately agree, strongly agree, or something like that, and you've got this 7-point scale or something, it might make sense to go anywhere like -3, -2, 1, 0, 1, 2, 3, or something like that, okay? And it might make sense to use numbers in that sense. But, and that implies an ordering, and that's fine, okay? And then if you only have 2 categories, then you can use numeric coding, and you can say one is 0 and the other is 1, and that also works if there's only 2 categories. But in most other cases, if we're talking about, like, the color of a car, okay, whether it's red, blue, white, silver, black, or something, it doesn't really make sense to represent this numerically. Okay. Although colors now, well, not now, but colors can be represented numerically using 3 light channels. And you can say the intensity of red light, or intensity of blue light, and intensity of green light. And we can represent all colors in the world using some skill that way, which is how our TV turns numeric values into colored pictures on the screen. But anyway, it's in probably most cases it's easier to think of colors as categorical. Okay. All right. So for logistic regression, we're going to code like if somebody defaults on their credit card payment as a 1 and not a default will be a 0. Okay. And now we're going to try to model the probability of someone defaulting based on the variable balance. Okay. And we're going to abbreviate this as just probability based on balance, okay? The probability function based on balance. And it's going to take on a value between 0 and 1. Okay, and then, you know, once we have this function, then we can use it for stuff. We can say, maybe we'll predict that if, excuse me, if the probability based on the balance is greater than 0.5, maybe that means we'll predict that they will default on their payment. Or, you know, if you're a bank and you're choosing who to approve loans for, maybe you'll say, you know what, if the probability of default is over 10%, don't let them open a credit card, okay? Or something like that, you know, who knows. Okay, if we plot the data, right? So anytime you plot some kind of categorical response, you're gonna just get like 2 strips of dots, okay? This is everybody with a 0 and everybody with a 1, okay, for different values of balance. And that you're not going to have, as far as whether they defaulted or not, you're not going to have anybody at 0.8, okay? Because they either didn't make the payment or they did, okay? You can't say I made 0.8 of a payment or something like that, okay? Doesn't work that way. So all the values line up. However, the function that we're trying to fit is, you know, going to be kind of this blue line here, okay? If we did just a regular old linear regression, fit a straight line, okay, this is kind of what we would get. And what we see is that this line goes below 0, and eventually if we trace this out, it will go above 1, okay? So as far as interpreting that to be, you know, what is the probability of something, then that doesn't make sense because you're going to have negative values and values over 1. Okay, so what logistic regression does is it basically takes a line that has a range from negative infinity to positive infinity, and then it basically just squishes it down so that it has a range going from 0 to 1. Okay, so you can imagine just this line, and then, you know, you're bringing it in a clamp, and it just kind of squishes the top down to 1, and the bottom brings it up to 0. Okay, so this is what we get with the logistic function. Okay, and so this is what the linear relationship might look like. So if we wanted to predict a numeric response based on one predictor, so this is based on simple linear regression, you've got your intercept, your beta 0, and your slope term beta 1, it'll look something like this, okay? If you put this into the logistic function, you get this, okay? All right, and so what we can see is that if this part, beta 0 plus beta 1x, is very negative, okay, so values that used to be very negative, okay, this e to this is going to be a value very close to 0, right? So you're rating e to the negative 100, okay? E to the negative 100 is 1 over e to the 100. That's going to be practically 0, okay? So this part is 0 divided by 1 plus practically 0, and then your probability is practically 0, okay? So for very negative values of beta 0 plus beta 1x, you get 0. And then if you have something very big, let's say this is positive 100, now you have e to the 100, that's a very huge number, and you divide this by 1 plus a very huge number, the same huge number, and you're going to get something very close to 1, like 0.999999999, right? Okay, and so for a very large beta 0 plus beta 1x, this value is asymptotically approaches 1, okay? And so we can see how this will have an output between 0 and 1, which makes it suitable for modeling probabilities, which are bounded between 0 and 1. Okay, so that's the logistic function. And we can do some math, right? We can take the log of this and rearrange terms. And if we do that, we can get this thing. This is called the logit, or the log odds function, okay? The log odds function turns this thing back into this linear form, okay? And this is what allows us to kind of make interpretations of, I guess, of our regression coefficients, right? So for linear regression, the interpretation was easy. You'd say if x increased by 1, then the output increases by beta 1, right? So whatever x increases by, you multiply that by beta 1, and we expect our output to increase by that much, okay? This time, if x increases by 1, then this function increases by beta 1, okay? And what is this function? This function is the log of the odds. The odds is the probability divided by 1 minus the probability. The odds are a weird thing, okay? Odds are, I don't know, if you guys have ever gone to Las Vegas or gone to a casino where you've played some gambling game, or you bet on a sporting event, then they don't talk about things in terms of probabilities, they talk about them in terms of odds. And they will say something like, I will give you 10 to 1 odds that, you know, this team will win the game, okay? 10 to 1, if you're giving someone 10 to 1 odds, then that means you think the team has only a 1 in 11 chance of winning, okay? And that, or you know, if they're offering, you know, 1 to 100 or something, basically the payouts are you bet $1, and if you are right, you get $100, okay? And on the other hand, if you bet $100, if you take the other side of the odds, you can bet $100, and if you're right, if they are right, then they get $1, okay? So there's $100 on the line, and they only gain $1 if they're actually right. But that just means it's kind of like an event that we almost expect to happen surely, but something like that. Okay. But anyway, so probabilities, I think we're accustomed to hearing probabilities and they're easy to understand. Odds are a little bit harder, and then log odds are like impossible to understand, at least at a practical level. Like we can understand them like theoretically, like, okay, you take the log of the odds function, like that kind of makes sense on a theoretic level, but practically speaking, I don't think our brains are made to understand this. Okay, so if we're talking about probabilities, we can talk about an increase of 5 percentage points. So we can say, you know, something has a probability of 20% of happening, and then maybe we do something and now we increase the probability of it happening by by adding 5 points to it, and now they have a 25% probability. That's easy to understand. What effect does this have on the odds? Okay, well, 20% probability is 1 to 4 odds. Okay, 1 to 4 odds, because basically it's 0.2 divided by 1 minus 0.2, which is 0.8, 1 to 4. So it means for every chance that it will happen, there's basically 4 chances that it won't. Okay, so 20% probability means it will happen 1 out of 5, 1 chance that it will happen, 4 chances that it won't. So that's the 1 to 4 odds. Okay, if we bump that up to 25% probability, okay, 25% probability is basically 1 in 4. Okay, so if I have 1 in 4, there's 1 chance that it will happen and 3 chances that it won't. And so we say that's 1 to 3 odds. So increasing 5 percentage points, going from 20 to 25%, changes the odds from going from 1 to 4 to 1 to 3, which means our odds have changed by 0.0833, okay, which is a little bit weird because we've gone from 0.25 to 0.333, so our odds have changed by 0.0833, okay? This is depending on what the original probability is. If the original probability is 90% and we add 5%, then it goes from 90% to 95%. That's not hard to understand, okay? But the odds change quite drastically. 90% probability is basically 9 to 1 odds, okay? If you got like 10 chances, it's going to happen 9 out of the 10, and 1 that it won't, so that's 9 to 1, okay? On the other hand, if you go to 95% probability, your odds are now 19, okay? 19 out of 20 that it will happen, 19 to 1, okay? And so your odds have changed by 10. They've gone from 9 to 19, okay? That same increase boost of 5 percentage points. Okay. Similarly, you know, the difference between 99% right and 99.9% correct is huge, right? So if you have if a company has if you have a manufacturing process and you've gone from 99% good products to 99.9% good products, that's a huge change. You're having basically 1 in 100 errors to 1 in 1,000 errors. And then going from 99.9 to 99.99 is now 1 in 10,000 is an error. And that's going to dramatically reduce. So there's a very big difference between 99% and 99.9% and 99.99% in terms of like failure rates or acceptability rates, you know. So I think air travel is like 99.9999 or something. But anyway, that's odds. And so, you know, logistic regression talks about a change in the log odds. And so here we have a change in the odds of changing by 10, but then the logit function talks about the log of the odds, which basically says instead of adding 10, you're going to multiply it by some factor. And so, you know, the log function changes you know, now we've got this, you know, kind of changes the relationship between adding and multiplying and switches those around. So it's weird. It's weird. Okay. All right. So anyway, we've got this, and the way we estimate the coefficients is done via maximum likelihood. Okay. But we're not going to worry about doing any maximum likelihood stuff ourselves. We just ask the computer, find the coefficients for me, and the computer uses maximum likelihood. And that's all we have to worry about. Okay? But basically the idea is we take all of our training data and we take in all of the x values and we plug them into this thing, okay? And so given a particular beta 0 and beta 1, we plug in all of our x values and we get the associated probability x, okay? And basically, for all the observations that did default, we want this value to be as large as possible. And at the same time, we need to balance it out by saying that all of the observations that did not default, we want this to be as small as possible, okay? So maximum likelihood, now we have to take everybody into account. We need to find the beta 0 and the beta 1. We got to kind of turn these two knobs. You know, one knob is adjusting the beta 0, one knob is adjusting beta 1. And what we want to do is we want to set them so that the probability of x is as big as possible for those that did default and small as possible for those that did not default, okay? And this is measured just by doing the total product of all of these probabilities here, okay? And I think this is all covered in 100B, so you get your estimates that way. And for us, the computer just handles this for us. All right, is that okay? That I just gonna say the computer does the coefficient estimating via maximum likelihood, that we're not gonna bother with any of the math ourselves? That's okay, all right. Okay, so if we do this in R, we'll load up ISLR, that's the library associated with our book. The data comes in this data set called default. And then we will fit a generalized linear model. And we say we want to predict default based on the balance. The data comes from the data set capital D default. Family equals binomial means it's a logistic regression, okay? So why do we use family equals binomial, okay? So we're talking about the error. The errors are either you got it right or you got it wrong, right? You either, which is basically a Bernoulli distribution. So it's not Gaussian. Gaussian is the kind of the family for linear regression. You're assuming that the errors are normally distributed. Here the errors are either you got the thing correct or you did not, okay? You got zeros and ones. And so that's going to be Bernoulli, which is binomial with one trial type of thing, okay? Okay, and so this is what we get. We get our coefficient for the intercept to be negative 1.06, and then the coefficient for the balance is 5.499 times 10 to the negative 3, so basically 0.0055. Okay, and it also calculates standard errors for each of these things because they are based on a sample, and so if somebody else took a different sample, they would have a different set of coefficient estimates, and we could imagine a sampling distribution, and the standard deviation of that sampling distribution will be the standard error. We can use a Z distribution to get our test statistics. And so anyway, we get p-values that are practically 0, okay? So we're saying that the balance does play a significant role and the intercept is significantly different from 0. So we do get p-values that are not 0. Okay, and so the coefficient estimate for the balance is, again, this value right here, 0.0055. It is significant. And so what that means is that if we increase the balance by 1 unit, if the balance on the thing goes up by $1, then the log odds of default increases by 0.0055, okay? Again, this is a weird thing. But it's kind of just, we have to talk about the log odds of default because the effect that it has is not linear. Wait, where did it go? Sorry, I'm looking for my picture. here. Okay. So in this thing, nonlinear means, increasing $1 on balance. Like if you go from 0 to, like, let's say we increase by $100. Having a balance of 0 and having a balance of 100 basically changes your probability of default by nothing. Okay, it has no impact on how much you will default by. However, in this zone, going from $1,500 to $1,600 changes a lot more. Going from $2,000 to $2,100 changes quite a bit. And then again, once you're at a certain point, adding $100 to your balance is not going to make a big difference. We're just going to, your probability of default goes from like 0.99 to 0.997 or something like that, right? So as far as the effect that it has on the probability itself, it's not linear, but it's linear if we're talking about the log odds of default, okay? So the exact interpretation of this value, it's a little hard to understand, okay? But it does tell us that the coefficient is positive, okay? It's 0.055, which just tells us that as the balance goes up, overall in the long, the trend is that the probability of default also goes up because it is positive, okay? And again, the summary table tells us that these values are significant, which means they are significantly different from 0. If they were not significant, then it means that the changes in kind of probabilities and rates, those could be explained away by random chance. But here we're saying the relationship we see between balance and probability of default cannot be explained by random chance. So this is what we've got here. Okay. If we wanted to make predictions in the computer, it's very easy. All we have to do is we just say predict, and we give it the name of the model that we're using to make predictions. And then here, we have to provide it basically the values of each variable it's going to use. So right now, there's only one variable being used to make a prediction, which is going to be balance. And so we can say, what's the probability that someone will default if their balance is 1,000? Okay. And so we say the new data is equal to, and then we throw that into a list because you could have multiple variables here. Okay. But here there's only one. So we say balance equals 1,000. The type is response. And it says they have a probability of 0.0057. So less than a 1% probability of defaulting if their balance is 1,000. Okay. However, if that balance goes up to $2,000, the probability of defaulting jumps up to around 60%, 58.5857. And then if their balance goes up to $3,000, then the probability of defaulting is now at 0.997. Okay. According to our data here. Okay. And just a reminder, this is kind of the distribution that we had on default based on balance, and we can see, at $1,000, most everybody did, not most everybody, but just this is kind of well within the normal range for those that did not default. And at 2,000, now we're kind of at the upper end for those that did not default, and those that did default are higher, and then 3,000 is kind of off the chart here. Okay. If you have a categorical predictor, we can fit logistic regression models as well, okay? So this time there's another variable called student, and student takes on the value yes or no. Is the person a student or not, okay? And so this is a categorical predictor. And so what R does, just like we saw for linear regression, is that it's going to take this categorical variable and make dummy variables out of it, okay? So in terms of student has only two things, so you're just going to have one dummy variable, okay? You basically get dummy variables for each category minus one, because then the last one is redundant, right? So in this case, you have yeses and nos, so you're going to get ones for the yeses and zeros for the no's in that case, right? If you had another thing where it was like, you know, what's your favorite color on the American flag, and it's red, white, or blue, you would have a column for red and a column for white, and then technically a column for blue, but the last one is redundant, so you would have two dummy variables out of 3 categories and so on, okay? But anyway, so here for student yes or no, we have a dummy variable for student yes, and we get a coefficient of 0.40489, okay, and this is significant. And again, so this is positive, and so what that tells us is that if somebody says, yes, I'm a student, okay, and we know nothing else about the person, then the probability that they will default is higher, okay? So again, yeah, we use dummy variable coding. The estimated coefficient is 0.4049. And so if we ask to make predictions for people who are students, the probability of defaulting is 0.04, and people who are not students, the probability of defaulting is 0.029. Okay, so it does affect the probability of default. All right, so that's logistic regression with a categorical predictor. Okay, we can do multiple logistic regression. And so just like for linear regression, we went from just using one predictor, okay, and we expanded it by adding more terms to the linear equation. We can do the same thing, okay? For logistic regression, for multiple logistic regression, we just expand this from just having the intercept and the slope to having multiple predictor variables, okay, up to p of them, and each of them have their own kind of slope value, okay, as far as the logit equation goes. And so if we turn that into the logistic equation, then we get this, okay? And again, to estimate this, now we have more values, and you use maximum likelihood estimation to get your estimates. And just like before, if you want accurate estimates of your coefficients, you're going to need more data. Okay, so if you have more coefficients, more terms to estimate, you're going to need more data to get an accurate estimate of these things. So this is multiple logistic regression, and so here we can make a model using all the variables in our data set. So in our data set for default, we have the 2 numeric variables, the balance that someone carries on their credit card, their annual income, and then whether they are a student or not, okay? The rest is the same data as default. Family is binomial. And here we're going to ask for the summary, and this is what we get, okay? So this, in our summary table, what do we notice? We have balance is positive, and it's significant. Income is positive, but it's not significant. Its p-value is 0.7, okay? So we're going to say it's not significant. And then student yes is negative, and it is significant. It's 0.006, okay? So its p-value is significant. All right, so so as before, coefficient for balance is significant and positive, and so that means having a larger balance is associated with a higher probability of default. Coefficient for income is not significant, so any difference that we see in the probability of default with those with higher or lower incomes, that can be explained away with random chance, okay? And lastly, for student yes, we have a negative value, okay? So back here when we did logistic regression on the categorical predictor and we only had student yes was actually positive, and we said if you're a student, you're more likely to default. Now we get student yes is negative, which tells us that if you're a student, it's less likely to default. So is there a conflict here? Okay. And so here, what this means is that if we keep the variables balance and income fixed, then being a student is less likely to default than a non-student, okay? So these are not in conflict. If we take a closer look at the data, this is what we will see, okay? So here, given a credit card balance, okay, the student line is in orange, and the blue line is for non-students, okay? And so the rate of default is higher indeed. The blue line is higher than the orange line, which means that if you're not a student, if your credit card balance is $2,000, you have a higher rate of default than the student, okay? Same for if your credit card is, balance is $1,600, it's higher up here than it is over here, okay? But what's going on? The reason why overall the default rate of students is higher than for non-students is that if you look at the credit card balances, the students overall have a higher credit card balance than the non-students, okay? And so because these, the students have a higher rate of credit card balance, or higher distribution of credit card balance, and credit card balance is associated with a greater default rate. Overall, if you don't take into account balance, it's going to appear that the default rate for students is higher than it is for non-students, okay? So does that kind of make sense, what's happening? So here we're getting a negative value for student, and over here we're getting a positive value for student. And it's because this one takes into account the balance. So given a certain balance, then then being a student makes you less likely to default. Whereas if we don't know anything about you and we just know that you're a student, then we can start to assume that you have a higher credit card balance. And knowing that you have a higher credit card balance will then make you more likely to default. Okay, so it's kind of an interesting thing. Okay, again, this is just simulated data, so I don't know if this is like this in the real world or not, but this just kind of illustrates how you can kind of have these confounding variables where you're not quite sure which is causing which, okay, and what's actually associated with what. All right, is this okay? All right, now technically there are methods to do logistic regression if you have more than 2 categories, okay? But it's not covered in our book, and we're not going to bother covering it, okay? So logistic regression, we're going to just say we're going to use for 2 categories only. But yeah, they do have, there's things like nominal, nominal logistic regression and stuff like that, more than 2 categories. Okay, do you guys want a break or not? Okay, all right, you guys, we'll take a 5-minute break here, okay? Come back at 1 o'clock, and then we'll do the rest of our chapter here.